Hello, and a very warm welcome to Kognito. Today, we're going to dive into a concept that's pretty much at the heart of how everything from our electric motors to our data storage actually works. We're talking about magnetic permeance.
So, to really get our heads around this, let's start with something we all kind of know. Electricity, right? We know electrical conductance is all about how easily electricity can flow through a wire. Well, magnetic permeance is pretty much its magnetic cousin. It's the measure of how easily a magnetic field, or what we call magnetic flux, can make its way through a material. You can almost think of it as a superhighway for magnetism.
So what exactly is magnetic permeance then? Well, in the simplest terms, you can think of it as the path of least resistance for magnetism. You see, a material that has high permeance is basically like an open door, just inviting that magnetic field to pass right through with almost no effort.
Okay, let's look at the official definition for a moment. Permeance, which we represent with a letter P, is the measure of the ease with which magnetic flux can be set up in a material. And that word right there, ease, is the absolute key to understanding this whole thing.
You know, this line from our source material just nails it. It's not about forcing a magnetic field into something, it's about how willingly, how readily a material just accepts it. Permeance is really a measure of this magnetic hospitality, if you will. Now, here's where it gets really interesting. There's a relationship between permeance and another term called reluctance. If permeance is the easy path, well, reluctance is the hard path. It's a magnetic version of electrical resistance. So it's a simple trade-off. High permeance means low reluctance, and high reluctance means low permeance. They're just complete opposites, two sides of the same coin.
So how do we actually measure this stuff? The standard unit is something called the Weber per Ampere-Turn. You might also see it measured in henries, which is a unit you might remember if you've studied inductance.
Now that we know how it's measured, let's see how it's calculated. And of course, there's a formula for it. This is the equation that lets us figure out the permeance of a magnetic circuit. Don't worry, we're going to break it down piece by piece. All right, let's look at what's going on here. First, A is the cross-sectional area of the material. Just think of it as how wide our magnetic highway is. Then we have L, which is the length of the magnetic path, or how long that highway is. And finally, we have mu, which stands for the permeability of the material itself. That's just its natural ability to support a magnetic field. So you see, a wider, shorter path made from a highly permeable material will give you the highest permeance. Simple!
Okay, so let's shift from the theory to how this is actually used in the real world. Engineers don't just calculate permeance for fun. They use a related value called the Permeance Coefficient to make really important design decisions.
This coefficient is basically a ratio that tells you how a magnetic circuit is behaving in a specific situation. It gives engineers what they call the circuit's operating point, and that is absolutely crucial when you're trying to design something like, say, a permanent magnet motor. So all of these properties, permeance, reluctance, operating points, they all lead us to classify materials based on their, let's call them, magnetic personalities. And this is where we get the difference between magnetically hard and soft materials. But to really get this difference, we need one last term, intrinsic coercive force. And what is that? It's basically a measure of a material's magnetic stubbornness. It's all about how well a material can hold on to its own magnetism and fight off any external field that's trying to weaken it. And this is where it all comes together. Materials with a low coercive force or low stubbornness, we call them magnetically soft. They are super easy to magnetize and, just as important, easy to demagnetize. They're perfect for things like transformer cores. But materials with a high coercive force are magnetically hard. They are really tough to demagnetize, which makes them absolutely ideal for creating permanent magnets that are built to last. So let's do a quick recap. What are the key things to remember? First, permeance is all about the ease of setting up a magnetic field. Second, it's the direct opposite of reluctance, which is magnetic resistance. And third, that stubbornness factor, coercive force, is what helps us classify materials as magnetically hard or soft. And that just leaves us with a final thought to chew on. Understanding all of this isn't just for a test, you know? It's the very foundation that lets engineers design the incredibly powerful motors in electric cars and the delicate data storage inside your computer. So the next time you use any of these things, just think about the amazing magnetic principles at play. I really hope you enjoyed this journey into magnetic permeance.
If you found it helpful, please do subscribe to Kognito, and don't forget to like and share this with anyone else who might be curious. Thank you so much for watching, and I'll see you in the next one.